Here we have the basic components of the DNA structure, which we're now going to assemble into a spiral. Let's see, first I should show you that I went ahead and I made triplanes, giant triplanes, so we can pivot these molecules. And now I will put them all together. So let's go into phase style X-ray and connect this here, the deoxyribose with our base pair. That's good enough. And then I'll go over here and I will connect this phosphodiester to the number 3 carbon on this deoxyribose. Get in real close, make sure we do this right. The center, and we will align it with that center. And now, looks like everything is connected. So let's make this into a big component. The base pair, the deoxyribose, and the phosphodiester, we're going to make them into a component because I'll explain later. Anyways, here we have a name requested for this component, and we're just going to select the default because we're moving fast here. Okay, now I've made a little pole here for stacking our base pairs. Let's move this over here like so. And did I do that exactly perfectly right? Just maybe. Yeah. Okay, so this bottom base pair is aligned with the x-axis, and now we're going to put a base pair on top of it as part of a spiral, and we'll use this pole for stacking purposes so everything is aligned. Okay, so there's our second base pair, and we're going to put this on top of here, but first we have to twist it the right amount for the spiral. So how much do we twist it? Well, to Wikipedia. Here's the DNA article, and here's the subsection on supercoiling. And it says here, with DNA in its relaxed state, a strand usually circles the axis of the double helix once every 10.4 base pairs. And as you can see from this picture here, DNA can be tightly wound, or it can be almost straightened out to a ladder, I suppose. But anyways, in the relaxed state, it's 10.4 base pairs for a complete turn. So let's go to our little calculator here and divide 360 degrees by 10.4 base pairs per turn, and that gives us 34.6 something or other degrees. We'll round it down to 34 degrees because we don't have to be too accurate. I mean, it varies so much naturally. So now we're going to rotate this box by 34 degrees. Go right here and twist it 34 degrees. Now there we go. We're happy. Now we shall bring this in like so. And there we have it. We now have two base pairs stacked on one another. But is this the correct distance? Probably not. I'm going to lower it down like so. And then I'm going to see if I can get this phosphodiester to connect. I want this atom right here to connect to that loose end of the bond, because this is our number 5 deoxyribose carbon in the upper bond, and this is the phosphodiester that's coming from below. So we'll want to get there. So how do we do that? Well, we're selecting the bottom base pair when I do that, and now I want to edit the component. So I click there, and now I click on this, and now we're using the box that the phosphodiester comes in. So we just tilt this up like so. Is it getting there? No, it's not. It seems like no matter what we do, we're not going to get that box there. I don't know what's wrong with this X-ray view, but there. for some reason this was giving the impression in X-ray view that this oxygen was behind this hydrogen, and it's not, obviously. But we still can't get there. So you know what we're going to have to do? We've messed around with the height of this base pair, and we've messed around with the phosphodiester. Yeah. And now we need to mess around with the deoxyribose. So I'll go down there. And I'm going to tweak this a bit. And you can tell maybe this isn't an exact science. It's more like an art. So there. Now I'll go back into base style X-ray, because I'm going to have to reconnect this. And you know, you could put the phosphodiester into a great big group with the deoxyribose, and then you'd go into that group to adjust the phosphodiester individually, and that way it would always stay connected. But I thought that was like asking a little too much for a little series on making molecules, and I don't think it's really needed. You know, it saves a little bit of time, but maybe for our purposes it's not that big a deal. Okay. What do I need to do here? I need to bring this over like so. Am I getting closer? Yeah, I think I am. You can see that with all the lines it's kind of confusing. Oh, we don't even want that one there. We want this one over here to go there, don't we? Because this is a double bond. We don't want that double bond there. It looks like it's still, it looks to me like this is still too high. So I'm going to go back here. I get out of all the different boxes, and now I'm moving the base pair. I'm going to move this down a bit. I'm going to move it right there and see if that works. Oh, that does work. So now I will click on this, and then I will edit this component. By the way, if you don't like the way these things are tilted, if you don't like the way the phosphodiester box is tilted, you can always explode the group and then make a new group, and now it's contained. Now this new box for the phosphodiester is aligned with the XYZ axis of the workspace. That might make things a little bit easier. Let's see how we're doing there. Oh, that does it. I do believe that does it. Let's back out of all the boxes and then turn off X-ray. And yeah, so we have our deoxyribose connected to a phosphodiester connected to a deoxyribose in the one above. I think I said I was going to explain why we chose a component instead of a group. It's because when we're adjusting the deoxyribose here, this one automatically changes because it's a component. This base pair is a component with this one, so it automatically changes. So we've got the structure here for part of the spiral, and from this we can build the rest of the DNA molecule, and that's what we'll do in the next video.